Greetings. Let's see if we can combine what we know about data types with what we know about category theory, because we have seen that category theory is a good way to structure how we think about things. So on the data type side, we had this data type of data types, or rather data type descriptions, and a way to turn a description into the arguments of the constructor of the data type it represents. And then when we define this operation, we didn't know what data type it described yet, so we had to take an X placeholder for the thing we wanted with an instantiating with this thing, right? And the first link we saw between this and category theory was that this args operation is actually functorial. So if I have a function from x to y, then I can extend that to a function from args x to args y, right? But in a way, that was almost an accident. So let's see if we can understand what is really going on here. And for that, let's move over to here and see. So what we have is args of, let's just think of the natural numbers for now. So I have args of n, and then I have this constructor, which goes into n, right? But of course, there's nothing really special. Well, there is something special about n, as we will see, but it does make sense to plug in different things instead of just n here. So in general, I can look at args of x for some set x, and if I am lucky, then I get an f from args of x to x. So what this means is that I have a way of interpreting 0 and successor into x, right? That's what this f is telling me, basically. So now, if I want to understand this, then I'm trying to make a category out of this. So I'm saying that my objects in this category are things that look like this, and I have to come up with a good notion of morphism. So this is called the category of args algebras. And there's nothing special about this args functor, of course. So if I have any functor f from C to C, so it has to be on the same category because I want to have this object and this object in the same category, right? So it can't be a general functor from C to D. But if I have any functor from C to C, then I can look at the category of F algebras. And the objects here are exactly one of these. So it's a choice of an X and then a so-called constructor F. So it's X and F from Fx to X. And what are the morphisms? So let's say that I have one of these and I have another one. So like this. Got this x prime, this f prime. Well, it's quite natural to ask for morphism between the underlying objects, right? So morphism from xf to x prime f prime is, let's say, alpha from x to x prime. So this is my alpha, like this. And then when I've drawn it this way, it's really tempting to complete this square and put something here as well, right? And what can I put there? I can't put alpha directly, but I know that args is functorial, or in general that is f is a functor. So I can look at the action of args on alpha, and it's going to go exactly from args of x to args of x prime, right? So it's an alpha like this, such that this diagram commutes. So let me draw it again. I have f of x to x. I have f of x prime to x prime with an f prime. And then here I have alpha. Here I have f of alpha, by which I mean the f map part of f, right? I want this to commute. So let's look at what this means for the natural numbers, where we had this args functor, right? So we said that args of x was a choice of a Boolean, which told us if we want to be 0 or successor. So if the Boolean is true, then we want to be 0, so we have no more arguments. And if the Boolean is false, then we want to be successor, so we have one more argument, right? So now we did have this constructor for the natural numbers, right, which send false and tt gets sent to 0, and true and n gets sent to suck of n, right? But now we see that if I have any x here and any f here, then I always have a notion of a 0 in x, right, which is whatever f sends this to. So I can always define my 0 in x to be f of false and trivial. And similarly, I can always define a suck in x, which goes from x to x, by saying that suck x of n is whatever f sends. I guess I screwed up my false and true. If it's true, then we should be in the then branch. So here, if it's false, then we have to give another x, which is what this n is, right? So in any algebra, which is what these things are called, right? In any algebra, we always have a 0 and we always have a successor. So now, what does it mean for this diagram to commute? If I have an alpha here and args of alpha. Well, there's only really two things I can put up here, right? I can either put true and tt, or I can put false and some x, right? So let's see what happens if I put true and tt. Well, if I go this way, then I'm going to get the 0 in x, right? It's going here. And then I go down with alpha, and I get alpha of 0 in x. And if I go this way, if you remember what this functor is doing on this b, which has nothing to do with the x, and this true, which has just the final thing, then we remember that it's just leaving it alone, right? So this gets sent to true and top again. And now if I go across with f prime, then I'm going to get the 0 in f prime, right? X prime. So we see that alpha preserves the 0. That's what that says. And similarly, if I start with a successor, then I'm going to get that alpha of the successor in x of n is going to be the successor of x prime of alpha of n, which you can see by just chasing false and x, or false and n through this diagram, right? In two ways. So what we see is that a morphism of algebras is exactly an alpha between the underlying objects that is preserving all the structures. It's preserving the 0 and it's preserving the successor, right? So this is quite a natural notion of morphism between algebras.